Hi, my name is Zhiyang, and today I'll be sharing about my FYP project on speech motion recognition using WaveNet architecture. Traditionally, speech motion recognition models tend to rely on complex preprocessing pipelines to extract certain audio features such as MFCCs. More recently, there has been a rise in the use of recurrent neural networks for such audio-related tasks as they are able to capture long-term dependencies. However, these tend to suffer from long training times due to their inability to perform parallel training. These pipelines also often lead to a lot of additional computational overhead as well. So the objective of our project is to come up with a model that can learn from raw audio waveforms without relying on recurrent networks and a minimal amount of preprocessing. We propose to use the WaveNet architecture to perform speech emotion recognition and to use MEL spectrograms as auxiliary features to better enhance the learning capabilities of our model. So, what is WaveNet? WaveNet is originally a generative model that can produce human speech by learning from large volumes of raw audio waveform. The architecture utilizes three key concepts, namely dilated causal convolutions, gated activation functions, as well as residual and skip connections. What are dilated causal convolutions? Dilated causal convolutions are a way to improve the receptive field of standard convolutions without increasing the computational cost by too much. Causal convolutions are done on the time domain instead of space domain that we are familiar with. By skipping input values at certain steps, we are effectively increasing the receptive field of the convolution process without increasing the computational cost. Gated activation functions rely on a combination of tangent and sigma activation functions instead of the traditional ReLU activation function. This has been found to perform better in the original WaveNet model in terms of conversion times. A large problem in deep layered neural networks has often been the time required for convergence as well as vanishing gradients. To prevent these issues, we utilize residual and skip connections to propagate the outputs through the layers. The key ingredient that we're investigating for our project is the use of external conditioning in WaveNet. WaveNet allows us to introduce a time series as the conditioning input on top of the raw audio waveform. We extract the MEL spectrogram from the raw audio waveforms and upsample it using a transposed convolution network to match the length of the original waveform. By applying this conditioning feature, we look to improve the performance of the overall model. Our model architecture is basically made up of a WaveNet encoder and a CNN network. We first extract the MEL spectrogram from the raw waveform. Then we input both the spectrogram and the audio waveforms into the WaveNet encoder. The purpose of the convolution neural network is to downsample the extracted features from the WaveNet encoder and to perform classification to identify the prominent emotion found in the speech sample. To evaluate our model, we use two key metrics, mainly weighted and unweighted accuracies. To simplify things, we name our proposed model EmoWave Plus. We then compare it against EmoWave, which has the same model architecture, less the spectrogram input. This is to see if the external conditioning is helping the model perform better. We then compare these against a recurrent network that learns from raw audio waveform as well, namely the 1D CNN LSTM. We train these models on two popular SER datasets. The EmoDB is made out of 10 German speakers with 7 different emotions, namely happy, sad, bored, fearful, angry, disgusted, and neutral. The RAFDES dataset is made up of 24 English speakers with 8 different emotions, namely happy, sad, angry, fearful, surprised, neutral, calm, and disgusted. We then perform speaker-dependent and speaker-independent experiments. Speaker-dependent experiments perform a completely random shuffle of all audio samples and do a fair 60%, 20%, 20% split for training, testing, and evaluation datasets. For speaker-independent experiments, we pick 60% of the speakers for training, 20% of them for testing, and 20% of them for evaluation. The main point of speaker-independent experiments is to see how the model performs when it has to evaluate a speaker it has not heard of or seen of before. This is the true measurement of how well the model can generalize for functional purposes, or whether it has simply overfitted to the provided data. Due to the size of the datasets, we perform both experiments using the k-fold cross-validation. These are the results for all experiments combined. As you can see from the results, the ImoWave Plus model consistently outperforms both other benchmark models throughout all the experiments. Our model is able to have a high accuracy without having to rely on recurrent layers. The introduction of MEL spectrograms as an additional external conditioning also increases the performance of the model by about 2% for all different metrics. A key thing that we observed was number of trainable parameters for each model. The 1D CNN LSTM model had more than twice the number of parameters than our model. Having a lot of trainable parameters can be good for learning a complex problem. However, when training on a small dataset like our SCR corpus, this can often lead to overfitting issues, which is where the model starts to memorize the training dataset. This can in turn hurt the performance of the model on unseen data. In conclusion, we are happy to see that the use of WaveNet architecture in SCR has proved to be competitive against recurrent networks while reducing the drawbacks that come with these RNN models. In the future, we would like to investigate the introduction of other conditioning features such as speaker or gender embeddings. We can also look into fine-tuning the extraction process of our MEL spectrograms. Another key area we would like to look into is improving the robustness of our model to becoming more resistant to unwanted noise. Thank you.